Let us begin with a quiet mystery. How can something very simple, something as smooth and regular as a wave, be used to describe something that looks much less simple, something jagged, uneven, or sharply changing, as long as it repeats? This is one of the deep and beautiful ideas in Fourier series. At first it seems almost unbelievable. A smooth wave rises and falls in a gentle rhythm. It seems soft, regular, and predictable. But then mathematics tells us that by combining many such waves, each one simple on its own, we can recreate shapes that do not look wave-like at all. We can build repeating patterns with flat parts, steep parts, corners, and sudden changes. We can build shapes that look much more like blocks or ramps or teeth, unlike the soft rolling motion of a single wave. It is worth pausing over that claim, because it is the heart of the subject. Simple waves can combine to describe complicated repeating functions. Not approximately in some vague sense only, but with remarkable precision, and in a way that reveals structure that was hidden before. So the central question of this whole discussion is not only what a Fourier series is, but why it is reasonable that such a thing should exist at all. Why should waves be the right building blocks? Why should repeating patterns be understandable in terms of frequencies? Why should a complicated function be thought of as a mixture of simpler oscillation? Let us move slowly. A periodic function is simply a function that repeats itself after some fixed interval. If you wait long enough, the same pattern returns. Then it returns again, and again. Nothing fundamentally new happens after one full cycle. The function has a rhythm. There are many common examples in life that help fix this idea. The tides rise and fall in a repeating pattern. The details may vary a little in nature, but the idealized picture is periodic. The seasons return year after year in a cycle. Breathing has its own rhythm, inhaling and exhaling, repeating again and again. Sound is especially important here. A musical tone is built from vibrations, and vibrations repeat. When something vibrates regularly, it produces a periodic pattern in time. So periodicity means repetition. A function is periodic when it comes back to where it started, and then traces out the same path once more. It is worth repeating that. A periodic function is not just any function. It is a function with memory arranged in a loop. After one cycle, the future is just the past repeating. The graph does not wander forever into new territory. It returns, and because it returns, it becomes natural to ask whether this repetition can be understood through repeating waves. Now, among all repeating motions, some are especially basic. These are the sine and cosine waves. Even if one has not yet fully internalized their formal definitions, one can feel their importance. They describe the smoothest kind of back and forth motion. They arise from circular motion, from vibrations, from sound, from heat, from light, from many phenomena in physics and engineering. They are the standard models of pure oscillation. A sine wave or a cosine wave does one thing, and does it perfectly. It repeats in a smooth, balanced, regular way. No corners, no jumps, no roughness. Just rise and fall, over and over, with complete regularity. So if periodic functions are repeating patterns, and sine and cosine are the most fundamental repeating patterns, then one begins to suspect that perhaps more complicated periodic functions might be assembled from these basic ones. That is the first intuition. A complicated rhythm may be made from simpler rhythms layered together. A complicated repeating graph may hide within it several simpler oscillations occurring at once. This is a very important shift in viewpoint. Instead of looking at a function only as a shape drawn on a graph, we begin to look at it as a combination of ingredients. The graph is no longer just a picture. It becomes the visible result of several invisible waves cooperating. Let us pause and reflect. When you hear a musical note played by a real instrument, what reaches your ear is often not a single pure vibration. It is a blend. There is a main tone, but there are also higher tones mixed in. These extra components color the sound. They give richness, edge, warmth, brightness. In a similar way, a periodic function may have a main broad shape and then smaller oscillatory ingredients layered on top. This brings us to frequency. Frequency tells us how rapidly a wave repeats. A low-frequency wave changes slowly. It stretches over a long interval. A high-frequency wave oscillates more quickly. It packs more up and down motion into the same interval. And this is one of the most helpful intuitions in Fourier series. Different frequencies correspond to different scales of detail. Low frequencies capture the large-scale behavior of the function. They describe the broad outline, the general trend, the slow undulation. High frequencies capture smaller details. They add texture, finer adjustment, sharper transitions, more local features. It is worth repeating because it explains so much. Low frequencies describe the coarse shape. High frequencies describe the fine structure. When we combine them, we get a richer object than any single frequency could produce alone. Imagine sketching a coastline from far away. First you draw the broad outline, the large curve of the shore. Then, if you come closer, you add bays and peninsulas. Closer still, you add rocks and inlets and irregular edges. In a loose way, Fourier series works like that. The low frequency waves draw the broad coastline. Higher frequencies add the smaller features. Or think of sculpture. The first rough form is established by large cuts. Then finer tools refine the surface. Again, broad form first, detail later. In Fourier series, every wave has a role. Some set the foundation. Others refine it. So what, then, is a Fourier series? At the most intuitive level, a Fourier series is a recipe for building a periodic function out of basic waves. That word recipe is useful. It suggests ingredients and proportions. Not every wave contributes equally. Some may contribute strongly. Some only slightly. Some perhaps not at all. The Fourier series tells us which waves are present and how much of each one is needed. So if one periodic function has a strong broad oscillation and only tiny high-frequency detail, its recipe will heavily favor low frequencies. Another function with sharp changes will require more contribution from higher frequencies. The shape of the graph determines the balance of the recipe. Let us say that again in a slightly different way. A Fourier series is not just a statement that waves are involved. It is a detailed decomposition. It tells us how much of each basic repeating motion is hidden inside the function. It turns the function into a list of wave contributions. This is why the subject feels so powerful. It gives us a second way to understand the same object. One way is to look at the graph directly. Another way is to ask, what frequencies lie inside this graph? Those are different descriptions of the same function. One is visual and external. The other is structural and internal. And often the second description reveals things the first one does not. Now let us linger on the combination process itself, because this is where the mystery becomes believable. A single wave is smooth and gentle. But when two waves are added together, the result is already more interesting. Sometimes they reinforce one another. Sometimes one rises while the other falls. Sometimes their peaks align, sometimes they do not. Their combination can be wider in one region and flatter in another. Add a third wave, then a fourth, then more and more, and the possibilities become very rich. This is the principle of superposition. Superposition simply means that effects can add. If one wave produces one displacement and another wave produces another displacement, then together they produce the sum of those displacements. Nothing mystical is happening. We are simply stacking contributions. And yet from this very simple rule, extraordinary complexity can emerge. This is not unique to Fourier series. In many parts of mathematics and science, simple components combine to produce structures that look much more elaborate than the pieces themselves. But Fourier series gives one of the clearest and most elegant examples. It is worth repeating, the power does not come from each individual wave being complicated. The power comes from the fact that many simple waves can be superposed. Simple pieces, rich result. Simple oscillations, complicated pattern. Simple ingredients, unexpected whole. Now let us think about shapes that do not look wave-like at all. Suppose a function stays nearly flat for a while, then changes rapidly, then becomes flat again, and repeats this pattern. This looks nothing like a single sine or cosine wave. Or suppose the graph rises steadily and then abruptly resets over and over. Again, this does not look wave-like in the ordinary sense. And still, Fourier series says that these shapes can be represented through waves. How should we imagine that? We should imagine that no one individual wave is trying to imitate the whole shape. That would be impossible. Instead, many waves collaborate. One wave gives a broad rise and fall. Another adjusts the slope. Another sharpens a corner-like feature. Another corrects the error introduced elsewhere. Each added wave improves the fit in its own way. So when a square-like or sawtooth-like periodic function is built from waves, it is not because some single wave secretly looks square-like. It is because the cumulative effect of many waves can approximate the repeating shape with great faithfulness. This is a very important point for intuition. The whole shape need not resemble any single ingredient. A wall is not shaped like a brick. A melody is not shaped like one note. A text is not shaped like one letter. Likewise, a complicated periodic function need not resemble one of the waves from which it is built. Let us pause and reflect again. This is often the moment where understanding deepens. One stops asking which wave looks like the square shape, and begins asking how can many waves, acting together, reproduce that square shape. That is the better question. And once one asks it that way, the answer becomes more plausible. The broad part comes from low frequencies. The sharp edges demand higher frequencies. Final shape is distributed across the whole family of frequencies. Another soothing way to say this is that a function can carry information at multiple scales. The largest scales are slow and smooth. The smallest scales are rapid and detailed. A Fourier series separates these scales. It untangles them. It tells us what part of the function belongs to the slow structure and what part belongs to the rapid structure. This is one reason Fourier analysis feels so natural once it settles into the mind. It does not destroy the function. It reorganizes it. It reveals its layers. Now let us connect this to geometry, because the geometric viewpoint is one of the deepest. In ordinary analytic geometry, when we describe a point in the plane, we choose axes. One coordinate says how far in one direction. Another says how far in another. The axes provide a coordinate system. They give us a language for locating the point. In a similar spirit, a function can be thought of as living in a kind of abstract space. Not a space of points in the usual visual sense, but a space whose objects are functions. In that space, it makes sense to ask for coordinates too. What should the coordinate directions be? For periodic functions, the natural directions are the basic waves. This is a beautiful idea. Instead of using horizontal and vertical directions, we use oscillatory directions. Each basic wave acts like one coordinate direction in function space. Then the Fourier series of a function tells us its coordinates relative to these wave directions. It is worth repeating that carefully. A Fourier series is not only a sum of waves. It is also a coordinate description. The waves form a natural coordinate system for periodic functions, and the coefficients in the Fourier series are the coordinates of the function in that system. This geometric interpretation helps explain why the subject feels so orderly. We are not merely experimenting with arbitrary ingredients. We are expressing functions in a basis adapted to periodicity. A function repeats. Waves repeat. So waves are the right coordinates for the world of repeating functions. This is very much like choosing the right language for the problem at hand. If a situation is rotational, circular coordinates can be helpful. If a situation is periodic, wave coordinates can be helpful. Once one accepts this viewpoint, many things become more intuitive. For example, why do simple waves matter so much? Because they are not just examples of periodic functions. They are the elementary directions out of which other periodic functions can be built. Why do the coefficients matter? Because they tell us how much the function points in each of those directions. Why do higher frequencies matter? Because they correspond to increasingly fine oscillatory directions in the function space. Now let us come back to the listener who may be drifting in and out of focus. If attention has wandered, the central storyline is still simple. We started with the mystery that smooth waves can describe complicated repeating shapes. We then recalled that a periodic function is simply a repeating function. We introduced sine and cosine as the most basic repeating motions. We observed that low frequencies carry broad structure and high frequencies carry finer detail. And now we are seeing that a Fourier series is a recipe, or equally well a coordinate description, expressing a periodic function in terms of those basic waves. That is the heart of it. Let us continue by dwelling a little more on why the low frequencies come first in intuition. If a function has a broad hump over one period, then any attempt to describe it must first catch at that main hump. A low-frequency wave, because it varies slowly, is capable of matching the large-scale rise and fall. If one only used very high frequencies, one would get too much rapid oscillation and not enough global shape. So the low-frequency terms are often the carriers of the overall form. They are like the long brushstrokes in a painting or the foundation stones in a building. Then, once the broad shape is in place, discrepancies remain. The graph may need to become fatter in one region, steeper in another, more sudden near transition. These corrective features tend to require higher frequencies, because higher frequencies can create more localized or more rapidly varying behavior. Again, it is worth repeating. Broad form comes from slow oscillation. Fine adjustment comes from rapid oscillation. This layering of scales is one of the most important intuitions in all of Fourier analysis, and it helps explain why partial constructions already say something meaningful. Even if one uses only the first few waves, one often gets a recognizable version of the function. It may be somewhat rounded or imperfect, but the main character appears early. Then additional waves refine the picture. This gradual refinement is conceptually gentle. It suggests that understanding is built in layers. First the rough outline, then more detail, then more still. There is also a philosophical lesson here. A complicated object need not be understood all at once. It can be decomposed into simpler modes. Each mode is easy to grasp. Their interaction creates the whole. This is a pattern that appears throughout mathematics. Now let us think for a moment about why this matters beyond the beauty of the idea. If a function is described by its graph alone, one sees what it looks like. But if it is described by its Fourier series, one sees what oscillations it contains. That can be more useful. For sound, the hidden frequencies determine timbre and resonance. For heat flow, wave components evolve in characteristic ways. For vibrating strings or membranes, the natural modes are oscillatory. For signal processing, separating a signal into frequencies reveals structure, noise, and pattern. So Fourier series does not merely redraw a function. It reveals a second, often more informative description. One might even say that the Fourier point of view teaches us that every periodic function has an inner life. Outwardly, it is a graph. Inwardly, it is a blend of waves. That is the reinterpretation at the center of the subject. And it is worth repeating in a very plain sentence. A Fourier series lets us stop asking only, what does the graph look like, and start asking, what waves is it made of? That shift is the big conceptual gain. Now there is another subtle point that deserves common attention. When a function has sharp transitions, the wave description becomes especially interesting. A single wave cannot make a sharp corner. Its motion is too smooth. So to build sharpness, many high frequencies must cooperate. The sharper the feature, the more high-frequency content is typically needed. This matches a very general intuition: fine detail requires short scales. A blurred image can be described without much high-frequency information. A crisp image with sharp edges needs more. A slowly changing melody can be captured with broad structure. A sudden click or abrupt change requires faster components. So when a function has sudden or nearly sudden changes, its Fourier series reflects that by involving stronger higher frequency contributions. It is not magic. It is scale. Sharpness lives at small scales. Small scales are carried by high frequencies. Therefore sharpness demands high frequencies. It is worth pausing there because that chain of thought is simple and powerful. Now, if one listens very carefully, one may realize that we have been saying the same few ideas in many different forms. That is intentional, because the subject benefits from slow circling. Periodic means repeating. Waves are the basic repeating motions. Different frequencies correspond to different scales. The Fourier series is a recipe of wave contributions. Complicated repeating shapes can arise from superposition. And geometrically, the waves serve as a coordinate system for periodic functions. If those ideas settle, then much of the later computational machinery will rest on solid conceptual ground. Let us now spend a little longer with the geometric picture, because it can feel abstract at first, but once absorbed, it makes the whole subject more peaceful. Think of a space whose elements are not pointer arrows, but functions. In such a space, it is natural to combine functions by adding them or scaling them. Once that is allowed, one can ask the same questions one asks in ordinary linear algebra. What are the natural building blocks? Can every function be described by combining certain special ones? Are some collections redundant and others efficient? For periodic functions, the sine and cosine waves answer these questions beautifully. They behave like a basis, a family of building directions. To know a periodic function is to know how much of each wave direction it contains. This is why Fourier series belongs not only to analysis but also deeply to linear algebraic thinking. One is decomposing an object into basis-like components. One is choosing coordinates. One is expressing a complicated element of a space in terms of simple standard modes. Even if the formulas are absent from our discussion, the conceptual architecture remains clear. A function is an element of a space. Waves are a natural system of coordinates in that space. The Fourier series gives the coordinates, and from those coordinates, the original function can be rebuilt. Let us pause and reflect. That last sentence is extremely important. Nothing is lost conceptually. We are not replacing the function with something alien. We are translating it into another language and then translating back. Graph language on one side, wave language on the other. Same object, different description. And often the wave language is the more revealing one. Let us also know this something aesthetically satisfying. Periodic functions live on cycles. Waves are themselves cycles. So the building blocks are perfectly matched to the phenomenon being studied. There is no awkwardness in the choice. The basis fits the world. This sense of fit is one reason Fourier series feels inevitable once one has seen it enough times. Now, before we close, let us gather the main insights one more time slowly. We began with the mystery of how smooth waves can build complicated repeating shapes. We saw that periodic functions are functions whose behavior repeats after a fixed interval, like rhythms in nature, breathing, tides, seasons, or sound. We introduced sine and cosine waves as the most basic, pure, regular oscillations. We then understood that frequency measures how rapidly a wave oscillates, and that low frequencies capture broad structure while high frequencies add fine detail and sharpness. From there, the notion of a Fourier series emerged as a recipe. Each basic wave contributes a certain amount, and the full function is assembled from all these contributions. We emphasize that this is possible because of superposition. Simple oscillations can be added together, and their sum can have a shape very different from any one of them individually. We also reflected on square-like and sawtooth-like repeating functions, which do not appear wave-like at all and yet can still be built from waves because many waves cooperate across different scales. And finally, we connected the whole subject to geometry by thinking of functions as living in a space where waves form a natural coordinate system. In that view, a Fourier series tells us not merely what a function looks like, but where it sits relative to the basic oscillatory directions. So the final takeaway is calm and profound. A periodic function is not only a graph, it is also a pattern of hidden frequencies. A Fourier series lets us hear, in a mathematical sense, the waves inside the shape. It lets us reinterpret a function not by how it looks at first glance, but by the oscillatory ingredients from which it is built. And perhaps that is the deepest beauty of the subject. A complicated surface conceals a simple structure. A repeating shape can be understood through repeating motions. What first appears irregular can, with patience, be resolved into a quiet order of waves. Let us end there, with that unifying thought. Fourier series teaches us that when a function repeats, it can be decomposed into pure rhythms. The broad rhythms give its overall form. The finer rhythms give its detail. Together they produce the visible shape. And so, to understand the periodic function deeply, one may look not only at the curve itself, but at the hidden choir of waves singing underneath it.